Okay guys, a semi-long video here, not long, not short, just a normal one, talking about oxidoreduction, ATP, and why all that, why. So let's start. Oxidoreduction, you want to think of oxidoreduction as two sides of the same coin. An oxidation is when you have a molecule carrying electrons that's going to give them away. So what do you want to think about when you think about oxidation? Think about rust. Rust. Metal exposed to air will give electrons, so the metal will get oxidized and lose its electrons to the air molecule, creating rust. That rust then is shed because it's like flaky and crappy, and so more metal is exposed. And that's why when you have metal rusting, it can create failure points because more metal gets destroyed and there's not sound structure that's remaining. So think about rust when you think about oxidation, right? Whereas reduction is the opposite side, is when a molecule accepts an electron. So one or more electrons. So reduction, why do I remember reduction? Because think about the charge of that molecule here. That molecule can have a charge of whatever, like let's say N, and there it has N electrons, and now it has more electrons, which means its charge goes negative. It's reduced, right? So a molecule that is reduced sees its charge going negative. And so usually reduced molecules start with a positive charge, and we'll see that in respiration, NADH plus, NAD plus, sorry, FAD plus. Those molecules have a positive charge, and when they get reduced, they gain electron, and they become NADH or FADH2. They don't have anymore that positive charge. So reduction gets that charge lower. So if you start positive, you go towards neutrality or negative. If you start negative, you get even more negative. So that's how I remember reduction. Oxidation, rust. Reduction, reduce the charge towards the negative, so you accept electrons. Oxidation, you rust, you are flaky, you lose. Like think about a rusty metal, it's flaky, so it's losing parts of it, and you lose electron in oxidation. That's my little trick for you guys. Now that happens in those oxidoreduction take place in that protein transport chain, protein of electron transport chain that we talk in details about in respiration and photosynthesis. So in this case, all I want to talk to you about is electrons come from oxidized molecules. They are flaky, they lose some electrons. Those electrons are carried along that protein chain, and at each step, it loses a little bit of its potential energy, right? The electron. That potential energy that is lost is transformed into kinetic energy, and we'll see how it's used in photosynthesis and respiration. And at the end, a molecule is accepting those electrons, thus gets its charge diminished towards negative, so it's reduced. Okay, why would we do that? The whole point is to have energy. How do we create energy? While we carry it, well, usually we do this with ATP, adenosine triphosphate. It's the cellular energy currency as it's written here. Do you need to know all the formula? No, but do you need to know that it's adenine, ribose, the sugar is ribose, and then 3-phosphate here? What looks similar to that? If you actually in your mind just put 1-phosphate only, a sugar and adenine, that's a nucleotide, right? You just have 2 more phosphate back there. So adenosine triphosphate is a nucleotide, ATP. It's like what's in your DNA, but with more phosphate. And the energy comes from the break of the bond between the alpha, beta, gamma, and beta phosphate. Gamma, third, beta, it's Greek letters for A, B, C. So now that you know where the energy is coming from, what do you do with that energy? So how do you go from tri to diphosphate? Well, you usually do it with a hydrolysis. So if you put water in between those two phosphate bonds here, you break it, you release the phosphate, and you have some energy released. And it comes from that ATP losing its phosphate. So the potential energy of that bond becomes kinetic energy. In the case we just talked about before, that was hydrolysis synthesis. In the electron transport chain, we liberate kinetic energy and we use it to attach a phosphate the other way around to an ADP with that kinetic energy to create ATP, and then the ATP is carried around to go through hydrolysis somewhere else. Fair, but ATP is not really stable and not really handy to transport. So usually, the way the cell works is to use phosphorylation. And phosphorylation is when an ATP molecule gives its phosphate to a glucose, activating it. And that's going to be heavily used in respiration, in glycolysis, Krebs cycle, and all. So we'll talk a lot about it, and that's what we mean by it. ATP, by hydrolysis, loses the gamma phosphate, gives it to the glucose, so that kinetic energy released from breaking ATP into ADP is used to attach the phosphate group to the glucose. There is some energy loss all the time, remember, but some potential energy has been added to that glucose molecule that can then be used somewhere else. And glucose is really handy to move around. The body knows how to do that really, really well. Why do you do all that? Why would you move glucose around with phosphorylation? What's the whole point of it? Look at the muscle video. Look at how those little actin and myosin fibers move. And I know I mentioned that before, and you probably looked at the video already. Look at it again now that you understand ATP, ADP. Look at how the muscle works and how thousands of tiny hands are playing a tug of war, pulling on those ropes to get the muscle moving. It's fascinating. And I will leave it at that. And you guys take care. I'll see you next week.